check out the calendar here. Did not do this early morning stream. I'll just delete that. I got a little bit of breakfast in this morning, but I had a pretty lazy morning this morning. I was having a nice conversation with some friends on Signal, and what else did I do? I watched like a couple YouTube videos. One was on something that we were talking about last night on the stream, which is retention. It actually was a really good video on some of the science behind how people learn and retain memories. My takeaway is that I'm basically doing a lot of the stuff that they talked about in the video already. And the high order bit for me was mapping the things that you're learning into your semantic network of meaning. Like, if you can attach an idea or concept to something in your current framework of like thinking, that gives it much more importance, and you'll be able to retain that understanding and that memory for longer. You'll be able to retain that learning. And then he talked a little bit about recall, which is what I'm doing right now as I'm recalling what he talked about in the video. So this is me demonstrating some of the ideas in the video, but the exercise of doing that recall kind of reinforces those synaptic connections. So recalling information is exercising that connection. So recall is important in the process of learning. Sleep, he also talked a lot about sleep and how sleep helps with learning, which we talked about last night as well. So the video is really good. I won't bring it up on stream here because I just don't want to search for it. But if the chatter that was on last night wants to chat more about that, I might send him over to that. But yeah, we talked a little bit about that last night. The other video that I watched this morning was on test-driven development, which wasn't very helpful. It was humorous and entertaining. It was the stand-up podcast with the Primogen and Tej and Casey Moratori and some other guy, I forget his name. But they were talking about TDD, and I mean, I worked at a company where I did TDD every day, pretty much every day for like 8 hours straight for 4 years. So, and I've carried some of those practices along with me throughout my career. So I'm very familiar with TDD and its benefits and costs. There are costs associated with it. Why is this thing not working here? Why not on the internet? Yeah, okay. Why can't I refresh this? Inspect. And then console here maybe, and say like what? Document.location. How do I refresh? How do I refresh a tab in Chrome from the console via JS? It's definitely doing like stuff. Oh, there it goes. I got it to go. I don't know why it wasn't refreshing. Alright. All this to update these things. Alright. I don't even know how this got messed up. Okay, so yesterday I think I got in like what? No, that's not yesterday. 21. I got 2 streams in yesterday. So yeah, put a 2 here. I'm gonna put a 1 here for now. 0 there. Gotta do my cardio today. I gotta do HIIT today. Yeah, that's a big thing that I need to do today. And I have a meeting at 1:30. I don't want to be dead for the meeting, so maybe I'll do my HIIT. kind of want to do the hit here and then do my lunch beforehand, which means that this morning session here can only last, I'll do 30 minutes for lunch. So this will be 11:30. And then it'll go to just 12. Save. Okay, and then this I'll say only lasts for 2 hours. We start at 9:30. Nah, I'll just say start at 9. And goes to 11:30 maybe? No, 11. Well, we'll do 11:30, why not? Okay, there you go. So that'll give me like 30 minutes between my hits session. Actually, my hit session is actually only 30 minutes. So I don't know why I had an hour here. So maybe I'll do an hour for lunch, because I actually do need to go to the grocery store. Okay, thanks, Proton. Proton really needs to get better at reliability. It just throws too many errors. And like, the application is kind of jank sometimes, where you'll make a state change and it won't update the UI because it's busy doing I/O with the network I/O. And then once it gets confirmation from the server about the consistency of the I/O, then it updates the UI, and it's just like cart before horse type thing. So afternoon stream, we'll take off 30 minutes from here, so that gives us what, 2.5 hours? That should be good. So we'll get 2 streams in today. I'll go ahead and just mark those because I'll commit to that right now. And I got a meeting and a D&D session in the evening, so I think 2 sessions is pretty good for today. So I got my cardio I need to do, my hit, my fitness check-in, and brilliant. I did not do brilliant. I marked it yesterday and I did not do it, so I want to be honest here and say that is a 0. But I did do my fitness check-in, I'm pretty sure. I got off last night and I just got on my phone and zonked out, and I didn't get good enough sleep. I stayed up till like 10 again last night, and that's starting to cost me. Like, so this morning I also learned about low power DRAM, LPDRAM, LPDDR. Okay, so yeah, I don't need to do more reading about that right now. Alright, what was I doing? I was checking my fitness check-in if I did that. I'm not going to be doing that today because I didn't weigh in and I didn't measure my glucose. I actually didn't check in yesterday. I need to do that. I do have the data, but fuck it. And then 10 minutes on brilliant. I might do that in the afternoon. But this stream I wanted to resume working on the ELF stuff. Actually no, I was going to resume learning Linux binary analysis chapter 3 Linux process tracing with ptrace. So I'm gonna do that. But yeah, I'm gonna take a quick bio break here, and I'll be back in like a couple minutes to resume that. All right. So let's go over to maybe here and start reading about Linux process tracing, which I'm somewhat familiar with, just learning about ptrace. That is a awful man page line length. All right, Linux process tracing. Let me put some light on here and off this, and then we'll start. Boom. Linux process tracing. In the last chapter, we covered the internals of the ELF format and explained its internal workings. In Linux and other Unix-flavored operating systems that use ELF, the ptrace system call goes hand in glove with analyzing, debugging, reverse engineering, and modifying programs that use the ELF format. The ptrace system call is used to attach to a process and access the entire range of code data stack heap and registers. Since an ELF program is completely mapped in a process address space, you can attach to a process and parse or modify the ELF image very similarly to how you would do this with an actual ELF file on disk. The primary difference is that we use ptrace to access the program instead of using OpenMMap read-write syscalls that would be used for the ELF file. With ptrace, you can have full control of the program's execution flow, which means that you can do some very interesting things ranging from memory virus infection and virus analysis detection to userland memory rootkits, advanced debugging tasks, hot patching, and reverse engineering. Since we have entire chapters in this book dedicated to some of these tasks, we will not cover each of these in depth just yet. Instead, I will provide a primer for you to learn about some of the basic functionality of ptrace and how it is used by hackers. I did want to go back and read the ELF parser code that we skipped over in last chapter because that's relevant to the work that I'm doing now with the ELF thing. One of the things I should fix is with my usage on no BSS, right elf. There was a usage, and I forgot to do that. No CC vim read elf, or sorry, write elf usage. Oops. Okay, I just fixes up that stuff. Okay. So do a stat into a stat structure. And then we do an mmap on the size to get it in. Mark it as private. Offset 0. We find the string table for the section header name with E. Okay, as a field, E shared string index gives the index of this of which section holds the string table. Okay, so a section can be a table. Okay, it makes sense. And then we assign that into this variable called string table, which is just a char star. We say, hey, mem is just a raw memory, and then we index into it by the shared interesting. So the elf headers section header string index is the index into the section header for the table, and then that has a sh offset, which is where the actual section is located. So the section header table is just a table describing the sections in the binary, and they have an offset. We read that offset, we index into the memory, and that gives us our string table. String table could just be it's stored, or it's represented as a type char star in this program, but it could be multiple null delimited strings in a series, or it could be a table, like a array of pointers to char stars. I guess we'll see how they access it. So it says print each section header name and address. Notice we get the index into the string table that contains each section header name with the sh name member. Okay. So we're going over all the elements of the section table using sh num in the elf header. And then we index into the string table. We index into it into the actual section headers, we get the name. The name is the offset into the string table for the name. And then we also get the adder. That makes sense. Okay. So string table, it's a char star, but it's not a string. It's multiple strings in a series, and there's an index that you use to index into it. And char star is just like the base address. And then we print out the program headers by iterating over pnum or phnum. And based on the type, we do different things. If it's a load, we know that text segment starts at offset 0 and only one other possible loadable segment exists, which is the data segment. Interesting. The text segment starts at 0. That is not the case in my program. We had 3 loadable sections. If you go back here and just do a read elf on, we'll do A for 0, 0 build, and we'll just do like write elf, or we'll do main. So there's 3 loadable sections here. The one that starts at 0 is this, basically it's the elf header, the program headers, and then a little bit of space after that for something else. I forget. I did document that. Right elf. I think it's here. Yeah, it's this build ID note. There's some data for the build ID that's stored after that. So all that 3 tuple of information is the first n bytes of the file, and that's mapped into address 0. So he's not correct in that, in this situation at least. The way Clang LVM zigcc compiles things, it does not put the text section at address 0, or it does not read from address 0 for the text section. It looks like this is the text section here because it has execute bit, and it's at 401,000 hexadecimal, and it starts at 1,000 in the file, and it goes for 60. So yeah, not exactly what his program does here. There's a case, there's a program header type, or segment type I should say, called interp, which is the interpreter. Which you can just get the offset and convert that to a char star, and that gives you the string for the interpreter. So that's just like literally saying, hey, this is where the string is located at. And then there's a note, and that has a virtual address. And the virtual address and the physical address are the same, which is interesting. I could see that working for the build ID. Oh, in this case, no, the virtual address and the physical address are not the same. They're offset by this 4 here. So this is going to be part of wait a minute. This is going to overlap. These segments are overlapping. It's interesting. Then there's a dynamic segment and a PHDR segment. I've never heard of that. I think that's if you exceed the maximum number of program headers that you can have in, I think it's like FF or something. It's some value. If you exceed that maximum value program headers, that's when you use a program header segment to kind of say, hey, we're going, instead of putting the program headers immediately after the elf header, we're going to put the program headers in a segment somewhere, and it could be arbitrary sized. Okay, so their code was not too crazy. It was just simple read elf. What we're doing currently in our NoCC project is far more advanced than what they had in that chapter. So that's good to just revisit, because when I first read it, I was just like, I don't really want to read this right now. And having done the elf stuff, now I'm just like, okay, that was easy. The importance of ptrace. In Linux, the ptrace system call is the userland means of accessing a process address space. This means that someone can attach to a process that they own and modify, analyze, reverse, and debug it. Well-known debugging and analysis applications such as GDB strace and ltrace are ptrace assisted applications. The ptrace command is very useful for reverse engineering and malware authors. It gives programmer the ability to attach to a process and modify the memory, which can include injecting code and modifying important data structures such as the global offset table for shared library redirection. In this section, we will cover the most commonly used features of ptrace, demonstrate memory infection from the attacker's side, and process analysis by writing a program to reconstruct a process image back into an executable. We demonstrate memory infection from the attacker's side and process analysis by writing a program to reconstruct the process image back into an executable. Oh, so we're going to take all the segments and like rewrite them into a file. If you have never used ptrace, then you will see that what you have been missing out. You will see that you have been missing out on a lot of fun. I have used ptrace in the past when I was learning about debuggers. The ptrace system call. I think I wrote some like test ptrace programs in C, but I was not super capable at the time in C, so now I am. C is such a nice language. Coming from Go, like my learning journey has been mostly, it actually started out in C, ironically. I was writing C CGI bins for old Apache web servers, like way back in the day, before dynamically typed languages were really popular. And I'd write these C programs and compile them, and you put them in the CGI bin, you mark them as executable, and then you could tell Apache, hey, exec this program by going to that path, /CGI-bin/ your program. And you could pass, like all the request headers were passed as environment variables into your program. So you'd have to read all the HTTP stuff from environment variables. It's a very strange interface. Common gateway interface, yeah. So I was writing C programs way back in the day. This must have been like, God, I'm so old. It must have been like 1999, somewhere around there, or 2000 maybe. It was 2003, I believe. Yeah. 2003, the summer of 2003, where I really got into PHP. And so my learning journey was like C, and then I did some I guess JavaScript, C were like two languages that I used extremely early in my learning about programming languages. And then I got into ActionScript and Perl. Those are the two languages that I was using, mostly for web stuff, because I was just interested in the web. So it's JavaScript, C, ActionScript, Perl. And it was like a very old version of ActionScript. It wasn't the more modern version of it, if it's even still in use. I think ActionScript is like a dead language now, pretty much. I'm curious, is ActionScript still used? Is ActionScript still actively being developed and used in industry? Or did the removal of Flash from the web effectively kill the language? Yeah. That's crazy that Flash is effectively killed. I guess it was the standards HTML5 movement in the early aughts. Not early aughts, the early teens, I should say. That really killed it. That and Apple not supporting it on iOS. I think those two things are like the death blows to Flash. Which is crazy because like when I was young, like Flash was like the only way you did interactive stuff on the web. Like JavaScript in HTML5 and CSS3 or whatever, like those things were like not capable enough to do anything really interactive. JavaScript is just like a toy little scripting language. Now it's all JavaScript. It's all standard stuff that's built into the browsers. Yeah. I think iOS not only not including Flash, but also iOS putting a competitive pressure on the web as a platform caused the web to like go through this transformation where they eliminated Flash. If you're deciding whether to learn or use it, don't. That almost makes me want to learn it even more, you know? I'm just joking. I spent too much time already on ActionScript in my life here. It's just crazy to me that there was so much creativity and content on the early web that was all Flash based, and we just went through this process of like killing it. I've never seen that before, and like Adobe really fumbled the ball. Could you imagine if Adobe got a standards body to adopt ActionScript in the browser as like a variant of JavaScript, or bridging the gaps between the two languages and like fusing them into one, and getting the bytecode interpreter into the browser? Like that like alternative universe where that happens, Adobe has so much more power over the web than they do today. And there's a pathway to compatibility with legacy Flash content that I guess currently today there's like compatibility shims with JavaScript that kind of like convert old Flash based content into like Canvas and HTML5 stuff. But yeah, Adobe really fumbled the ball. They had such a huge market share. Like everyone had Flash. Flash was like, it effectively came with the browser. Every website said, "Hey, download the Flash plugin," and then they just kind of like, what? I guess when Macromedia sold to Adobe, that's when the ball was fumbled there. I remember Quicksilver was like Microsoft's response to Flash, I think, which was C# based. I think it was C# based. Silverlight, Quicksilver, and Silverlight. I think those are some Microsoft technologies that were similar idea to Flash, but they never got mass adoption. I remember going to conferences. Must have been around like 2008-ish. 2008 to 2010, like that time frame where like Microsoft was pushing Quicksilver and Silverlight and all that stuff. And I remember at the time I was like, "There's no way I'm fucking like doing." I mean, I'd never been much of a Microsoft person, but there was no way I was gonna invest any time in that. It's so sad. But yeah, this is one of the languages I learned early on in my learning about programming was ActionScript. I remember I had to have been like in either 10th, I think it was 10th grade. It was like the summer going into 10th grade. So I would have been how old? 15 years old, something like that. I was learning about Flash and ActionScript. Adobe announced it's stopping Flash Player development for mobile. Around the same time, Apple had already refused to support Flash on iOS. This is when the industry realizes Flash and therefore ActionScript Flex has no feature on the most important new platform, mobile. Yeah, it really was mobile and iOS that killed it. Because Android had support for Flash very early on, and iOS just refused to implement it. And I don't blame them. Like, it was a fucking clusterfuck of security issues and performance issues and drained the device battery. It was an easy thing for them to not support, so long as they got like HTML5 video and hardware support for video decoding, fixed function support for video decoding. H.264, all that stuff. Flex is donated to Apache, basically signaling Adobe is done investing in it. Tooling like Adobe Flash Builder stops evolving meaningfully. Official death sentence is 2017. Wow. Adobe announced Flash Player will be end of life in 2020. At this point, no serious project would choose ActionScript or Flex. 2020 was its actual death. And then it's buried. Flash Player begins actively blocking all content. Browsers rip out support entirely. That's when it literally stops working for users. Yeah, so sad. All right, that was a nice trip down memory lane. But yeah, I was talking about C. So yeah, C. I learned recently. I started investing more into learning C much better. But originally, it was my first programming language. Then I went from C to Perl to PHP to Python to Go, and then from Go to what I'm doing now, which is a lot of C. So it's kind of, I come full circle. And the thing I really liked about Perl, which is like I was doing C and then I switched to Perl, is that I didn't have to compile. I hated compilation. I just wanted to like edit files on a CGI bin directory and then hit them on my web browser and not have to recompile every time I did that. There's just one less step that I had to go through. And so the dynamically typed languages had an advantage in that regard. And PHP, I switched to PHP just because I actually had a preference for Perl over PHP. I didn't like a lot of the PHP stuff because PHP was by design first a templating language. It was structured around HTML and providing server logic inside of your HTML using like little PHP tags. Whereas Perl was designed first and foremost as a programming language on the server that outputted HTML as one of its things that it could do. So, yeah, I guess I preferred the Perl's model over PHP's, but then I started learning PHP in 2003, like I mentioned. Summer 2003, my dad bought me a PHP book that I read cover to cover, and I learned a lot about PHP and MySQL. And after that, I was just like, okay, well, I'm not doing Perl anymore. It was very clear at that time that doing stuff on the web, you wanted to be using PHP and not Perl. And then Ruby and Python started getting really popular around 2007, or I guess a little bit before that. But 2007 is when I started looking at Python and Django and started investing in learning Python and Django. And then Flask came along, which is Armin's web tool in Python, which was super minimal and clean API, and that was really nice. And then I switched to using SQL Alchemy. SQL Alchemy is like a brilliant piece of software. And then I started doing some concurrent programming for power management system using Flask, and I don't think it had a database. Maybe it did, but it was Flask and Gevent. And I just had all these frustrations with managing Gevent. Like it was the best form of async at the time. Later, Python added async as like a first-class feature to the language, but at the time, Gevent was like a really nice async solution because it gave you this concept of like green threads, but they're all cooperative, and there's no concept of select from what I remember. And so I was just like really frustrated with like trying to write a program that could monitor like tens to hundreds of thousands of power management systems. And so that's when I started learning Go and using Go routines. It was just like, wow, this actually really works. It really performs well. There's a lot less complexity. Or the complexity that does exist is kind of like very nicely abstracted away from you. So if you don't want to deal with it, you don't have to deal with it. And the select keyword, I think the go keyword is my favorite in Go, but if I had a second favorite, it would be select. Because that concept just did not exist in Gevent from what I remember. And once I understood how select worked, I was like, oh, this is the thing that I wanted in G-Event that I didn't have. A way to like monitor multiple, in Go's case, they're channels, but multiple file descriptors, multiple things that you can be waiting on, and handle each one appropriately in a single thread as they become ready. So yeah, select is like a really cool language feature. And I don't see many languages with select built into the language. Go is just such a really awesome language when it comes to concurrency. Having Go, such an elegant, simple keyword, Go. And then you give it the function and the arguments that you want to provide to that function, fully evaluated. And it will execute the function in a Go routine, asynchronously, effectively, from your current thread of execution. And then channels. I mean, channels are kind of a natural thing to run into for message passing and signaling. They're basically a thread safe queue. So that's like a natural thing to add to a concurrent language like Go, or even to a regular programming language. It basically took the pthreads model and just made it perform much better in a modern environment where you can't block on I/O. I really should study Go's runtime at a much deeper level now that I have a better systems level programming background and understand like netpolar and the scheduler and stuff like a lot better from first principles, and see how they map concepts in the language to implementation. Because right now I look at it like strace dumps of all the system calls when I run Go programs, and I'm like, I understand what they're doing with the epoll, but I have an understanding for how they manage execution of Go routines. And the netpolar stuff is like, I understand in broad terms kind of how it works, but I don't understand in implementation details how it works. So it'd be really nice to get a better understanding of those things. So yeah, that's a bit of a rant. Okay, let's read more about ptrace here. So the ptrace system call has a libc wrapper like any other system call, so you may include ptrace.h and simply call ptrace while passing it a request and a process ID. The following details are not a replacement for the main pages. I think he meant to say man pages of ptrace, although some descriptions were borrowed from the man pages. Here's the synopsis. Yeah, this book is not very well edited. I find a lot of technical books are not very well edited because editors are not technical. Like, they see main pages and they're like, yeah, sure, that's it. You fed this into an LLM, they would catch it though. So that goes to show you how important AI is. Okay. Here's a synopsis. Include ptrace. So you have a enum ptrace request PID, a pointer to an adder, and a pointer to data. Okay, so enum is going to be the request type then. So ptrace request types, here's a list of requests that are commonly used when using ptrace to interact with a process image. Ptrace attach the process specifying a PID, making it a tracee of the calling process. Tracee is sent a sig stop signal, but will not necessarily have stopped by the completion of this call. Use wait PID to wait for the tracee to stop. Ptrace trace me indicates that this process is to be traced by its parent. A process probably shouldn't make this request if its parent isn't expecting to trace it. Ptrace peak text, peak data, peak user. These requests allow a tracing process to read from a virtual memory address within the trace process image. For instance, we can read the entire text or data segment into a buffer for analysis. Note that there is no difference in implementation between the peak text, peak data, peak user requests. Then there's poke text, poke data, poke user. So I understand what text and data would be. I guess user would be the entire address space, maybe. Poke text, data, and user. These requests allow a tracing process to modify a location within the trace process image. Get regs. This request allows the tracing process to get a copy of the traced process's registers. Each thread context has its own register set, of course. Set regs. This request allows the tracing process to set new register values for the trace process. For example, modifying the value of the instruction pointer to point to the shell code. ptrace continue. This request tells the stop trace process to resume execution. ptrace detach. This request resumes the trace process as well, but also detaches. ptrace syscall. This request resumes the trace process, but arranges for it to stop at the entrance exit of the next syscall. This allows us to inspect the arguments for the syscall and even modify them. This ptrace request is heavily used in the code for the program called strace, which is shipped in most Linux distributions. ptrace single step. This resumes the process but stops it after the next instruction. Single stepping allows the debugger to stop after every instruction that is executed. This allows the user to inspect the values of the registers and the state of the process after each instruction. ptrace get siginfo. This retrieves information about the signal that caused the stop. It retrieves a copy of the siginfo T structure, which we can analyze or modify with ptrace set siginfo to send back to the tracee. ptrace set siginfo sets the signal information, copies a siginfo T structure from the address data to the tracer to the tracee. This will affect only signals that would normally be delivered to the tracee and would be caught by the tracer. It may be difficult to tell these normal signals from synthetic signals generated by ptrace itself. Adder is ignored. ptrace set options sets the ptrace option from data. Adder is ignored. Data is interpreted as a bit mask of options. These are specified by flags in the following section. Check out the man pages of ptrace for listing. The term tracer refers to the process that's doing the tracing, the one that has invoked ptrace, and then the term tracee or the traced means the program that is being traced by the tracer. Default behavior overrides any mmap or mprotect permission. The default behavior overrides any mmap or mprotect permissions. This means that the user can write to the text segment with ptrace even though it is read-only. This is not true if the kernel is PAX or GRSEC and patched with mprotect restrictions, which enforce segment permissions, so that they apply to ptrace as well. This is a security feature. My paper on ELF runtime infection at so-and-so discusses some methods to bypass these restrictions for code injection. A simple ptrace debugger, process register, and flags. Okay, so they have an implementation of a debugger here. All right, process register, state, and flags. The user regs structure for x86-64 contains the general purpose registers, segmentation registers, stack pointer, instruction pointer, CPU flags, and TLS registers. I think out of all these, the TLS, so let's go to the first. General GPU registers, fully understand those. I don't think there's much mystery there. Segmentation registers. This was totally skipped in the CSAPP book, and so I really don't have much understanding how segmentation works with segmentation registers. The lecture that they gave on some of this stuff, the lecture basically mentioned that they're not going to cover it in the course or in the book because it's like a legacy feature of how memory was managed before virtual memory. But my understanding is that it's still used even outside of virtual memory for some purposes. So I'm curious what the segmentation registers are, how they work. I don't have a good understanding of that. Stack pointer, that's just another GP register. Instruction pointer, that's just a special pointer or special register for RIP in this case. CPU flags, R flags, that's going to be stuff for like, you know, conditional jumping, tests, compare, add, subtract, all those registers that get set for, or all those flags that get set for those instructions. And TLS registers. Quick chat with AI here. Let's do give me all the R flags on AMD 64 and their use. Yeah, so carry bit, parity, auxiliary carry flag. Yeah, binary coded decimal. I haven't dealt with binary coded decimal since an undergraduate course back in back in the day. Let's revisit binary coded decimal. I'm just gonna open up a browser here and search for binary coded decimal. I remember thinking at the time like this stuff is like jank. Class of binary encodings where each decimal digit is represented by a specific 4-bit binary nibble. So because a nibble can represent a nibble is 4 bits, so it'd be 2 to the power of 4. 2 times 2 is 4 times 8, yeah, so it's 16. Yeah, because it's like a hexadecimal digit. Hex digit. Easy conversion to human readable decimal in electronic systems and avoids rounding errors in financial calculation, but is less storage efficient than binary, using only 10 of 16 possible 4-bit combinations. So binary code, yeah, binary coded decimal. Yeah, you can see here like the ones are only used for 2 places here instead of which should be 8 places. So you're losing 6 values there that they just don't have a they're encodings that don't have values associated with them. Yeah, invalid codes because BC only uses 4-bit combinations. Binary values A through F are considered invalid, sometimes requiring correction steps during arithmetic operations. It's primarily used in digital systems requiring precise decimal arithmetic, such as real-time clocks, electronic meters, and 7-segment display drivers. I think I ran into it using 7-seg displays, because I did drive a 7-segment display in a computer engineering course in undergrad, but I haven't ran into it since undergrad. Easy conversion, simple to convert to decimal digits for display. Yeah, because the hex value is the same as the hex representation of it is the same as the decimal representation. No rounding errors, ideal for financial decimal calculations where binary float point errors are unacceptable. I don't understand why you need to use this over float. If you're using this, you could use easily binary, like just an actual like unsigned binary value. So I don't know why you would need to compare it against floating point rounding. I would imagine fixed point arithmetic or what they refer to as, what do they call it? What is the name of infinite? They call it infinite precision. Infinite precision arithmetic. Or arbitrary precision. Yeah, because it's not really, or they call it big num. Yeah, big num arithmetic. It's how precise you want to go is arbitrary. It's not infinite because computers aren't infinite. But it's sometimes referred to as infinite precision arithmetic. Okay. Yeah, I remember that being annoying. How is that? Oh, it's in binary. Okay. Yeah, and then 2 and 5 there. Yeah. It's easy to convert between binary coded decimal and decimal, basically, for human beings, versus converting between decimal and binary. All right, we can close out of that. Zero flag, sign flag, overflow flag. Control flags. So these arithmetic status flags I'm very familiar with. Control flag, except for this auxiliary carry flag, I'm not really familiar with that. Trap flag, interrupt enabled flag. Direction flag. I hate that the LM just like slops in a bunch of shit from my previous conversation that's totally irrelevant. I understand why they do it because they want like you to like, oh, you're paying attention and you're making connections to like older. It's like this stuff has nothing to do with that. In real world systems work, like what you're doing with ELF, start, etc. It's like, come on, get out of here. I don't need to read that. Okay. All right, I was just reviewing some of the R flags. And then finally, the thread local storage registers, I'm not super familiar with. Obviously, I ran into them, but I'm not really familiar with how they work. Okay, so if we look at the user reg structs, we got unsigned long, which would be 128. No way. A long int? Is that just a 64-bit int? Well, I have a program here that will tell me. If I jump over to KNRC, I think it's under chapter 02 here. Nope. Chapter 01 maybe. Yeah, here. Compare int sizes. So I don't have long in here. Let's update this. Vim test int sizes. Oh, and there's a size T that didn't commit here. Get status. Interesting. I didn't commit that. You can tell I'm coming back to this periodically. We'll say long. We do have a long. So long is 8 on all platforms. Okay, that makes sense. Okay. Okay, so we got our long, which is 64-bit. R15, 14, 13, 12, RBP, RBX, R11, R10, 9, 8, RAX, RCX, RDX, RSI, RDI. Then there's an original RAX. Not sure what that is. RIP, obviously, CS. So this gets into the thread local storage and segmentation registers. E flags, which is R flags, but I guess I didn't change the name of it. RSP, SS, FS base, and GS base. Those are the thread local storage ones. And then we got DS, ES, FS, and GS. In 32-bit Linux kernel, GS was used as the thread local storage pointer, although since x86-64, the FS register has been used for this purpose. TLS. Using the registers from user reg struct with read-write access to the process memory using ptrace, we can have complete control over it. As an exercise, let's write a simple debugger that allows us to set a breakpoint at a certain function in a program, and when the program runs, it will stop at the breakpoint and print the register values as the function arguments. A simple ptrace debugger. So this is going to actually write the trap instruction into the memory, and when it gets hit, it'll then print out the register values and function arguments. Let's look at a code example that makes use of ptrace to create a debugger program. So we got a typedef struct handle, and then we got a for declaration for a lookup symbol, and then we got main, which is rather long, expected, and then we have the lookup symbol defined at the end. Okay, so the first thing is this handle. No documentation as to what it is, but it does have the ELF header, program header, the section header, a pointer to bytes, which is the memory field, a symbol name char star, an adder for the sim adder, and then an embedded struct for user regs, and a char star for exec. And then we have our lookup symbol, so we give it the handle, and a char star for the symbol, and it looks it up for us, the location of it, which we're going to need to look up the symbol to set our breakpoint. Okay, so we go into our debugger program. We're just doing some argument parsing. There is a handle H, which exec gets assigned into handle. Yeah, okay, so the program string gets assigned into the handle exec. And then we move that into arg0. Not sure why we do that. And args is okay, so this is a different array. Okay, that's a local array. And then we assign in the symbol name, and then we open the program, we stat it, and we mmap it. We could then close it if we wanted to. We then assign pointers into the mmapped program based on the header's offsets. And then I don't think this needs to belong there. We do some validation on the ELF file, make sure it's executable. We make sure that there is a section index and a section offset for the section header table. We then look up our symbol, we assign it into our handle T sim adder. We then close our file descriptor, which we could have done earlier, I think. I don't think we needed to wait this long to do that. And then we do a fork. And if we're in the child, then we call ptrace trace_me. PID is wrong in that case, but we're going to do ptrace trace_me, assuming that that completes. Why does a child process need to call ptrace trace_me to be traced? Okay, so they pass in PID, but PID is 0, so it's effectively a null, right? So parent calls fork, child calls ptrace trace_me, child calls execve, kernel sends a sig trap to the child right after exec, which halts its execution. Parent debugger starts controlling it. Okay, makes sense. You want to do that. So in GDB, when I run the debugger on a program, it requires me. Hey, how's it going? There was a video I wanted to share with you that I ran across this morning. Let me pull it up here. I think it might be useful for you based on our conversation last night. It's about learning and stuff. Let me pull it up here. It's this guy that I follow on YouTube. His name's Justin Sung, I think it is. Yeah, here it is. Justin Sung, How to Read Once and Remember Forever. It was a recent video. Here it is. Okay.
You're struggling to focus. And this is your brain.
I actually used this Brain FM
In this video, I'm going to
for
teach
like a week, but just as a trial. And I guess it can be good, but I didn't feel like the value was there. How to Read Once and Remember Forever. Let me share this in Twitch chat so you can click on it. I'm not going to watch it again on stream, but I think you might get some value out of it. He touched on a lot of the stuff that we discussed last night, so I thought it was interesting. Yeah, like a lot of the stuff he talked about. He goes into some of the science, which I think is honestly questionable, but some of the actual ideas behind like how to better retain stuff, I think were pretty helpful, and things that I like naturally do.
emotional.
Let's see here. There was a slide that he had here. No, here it is. So this section here, you see, he talks about sleep, retrieval, semantic encoding and processing, integration, the novelty and survival value of what you're learning. These are all things that affect your learning ability. And then emotional salience. So he was saying like these two you typically don't have a lot of control over, is like your emotional salience of the material and the novelty or the impact it has on your survival. That's true to a certain extent, but I was like, well, if you relate what you're learning to having a huge impact on your financial career, your financial success, like that has a direct impact on your survival. You can kind of tap into that a little bit and say like, okay, I'm motivated to read this because and learn this topic because it has a huge impact on my survivability. You know? But yeah, he's saying like the studies say that those have a high impact on your ability to learn and retain information. Sleep you definitely have control over. And then these other things here, he said that, you know, you have control over, but I'll let you watch it. I'm not going to watch it again, like I said, but I thought it was like kind of interesting because he touches on a lot of things that we talked about last night. But yeah, learning about P-trace here. You did hit today. I can't able to time it right. I feel so weak after that. I feel heat in my body. Yeah, I mean, I have my hit this afternoon. I'm not looking forward to it. It sucks. I mean, it just sucks. Like my breathing gets really labored when I do hit. Like I get inflammation in my lungs sometimes. Like sometimes I feel like kind of like blood and stuff like in my lungs because I'm using my lungs so much. They're pulling in so much air and they're doing so much work that sometimes the lungs get damaged just because I need to breathe. if my lungs aren't affected, then usually it's like something else that hurts. Yeah, hit really sucks, but it's good for you. But yeah, I'm learning about more ptrace stuff here. So ptrace is the system call in Linux that allows you to get control over another process and do things that like a debugger could typically do. Almost all debuggers on Unix use ptrace. It's a pretty common system call. So I'm looking over his like implementation of a debugger here. He has like 4 pages on implementing a basic debugger. The first thing he does is he forks off, and he calls this ptrace trace me and the child, which suspends execution of the child. And I was curious because I wanted to like see if GDB can do that. So in GDB, when I run the debugger on a program, it requires me to type R to start the program. At the entry point, how do I halt execution but at the entry point instruction without setting an explicit breakpoint at that instruction? I want to stop right at the entry point before any user instructions run without manually setting a breakpoint on the address. There are a few clean ways to do it. Start I is exactly what you're asking for. It starts the program, stops at the very first instruction executed. Under the hood, GDB effectively does trace me plus exec flow, then halts on the initial sig trap from the kernel. So you land right at the, so I was not aware of this start I. Alternative run plus automatic stop on exec. So you say catch exec, run. Interesting. Slightly earlier in the life cycle than the actual entry point. So this probably be before the dynamic libraries are loaded by the loader. Yeah, I think that's probably what happens here. So if you do the catch exec, you're actually getting in before the entry point. The entry point is where the processor executes instructions after it's already done its dynamic loading. So you have like kernel stuff initially to fulfill the exec. Then you have a handoff into user space for the dynamic linker to do its business. And then the dynamic linker then hands off to your entry point on your program. So this actually gets in before the dynamic linker. That's pretty cool. Yeah, and I can't do symbol resolution because I stripped my binaries. Yeah, the run that's the problem. I want start I in most situations. Cool. I didn't know that. Okay. So this guy, he waits on the status from the child process, which will unblock when the child has exited, but it might also unblock when the child has done its exec. Let's read the man page for wait. So wait for state changes. It doesn't say exit. It says wait for state changes in a child of the calling process and obtain information about the child whose state has changed. A state change is considered to be the child terminated. That's the one I'm familiar with. The child was stopped by a signal. Okay. That would be the sig stop that gets sent by the kernel. Or the child was resumed by a signal. In the case of a terminated child. Performing a wait allows the system to release the resources associated with the child. If a wait is not performed, then the terminated child remains in a zombie state. If a child has already changed state, then the call returns immediately. Otherwise, it would block until either a child changes state or a signal handle interrupts the call, assuming that syscalls are not automatically restarted using the SA restart flag of SIGAction2. In the remainder of this page, a child whose state has changed and which has not yet been waited upon by one of these systems is termed waitable. Okay, that makes sense. I was only familiar with wait in the context of waiting for the child to exit, to terminate. So he's using it here to wait for the child to get the sig stop signal. So then now the parent has full control over the child, and they run ptrace peak text to look at the text segment, which is interesting because like I would just assume that like the text segment, like it isn't really, I guess a text section. There is no real text segment. There is a segment that contains the text section. Like if I run, let's run readelf all. Let me jump into nocc. Run readelf all on build or 00 main build main. Yeah. So the actual segments are here, and you can see none of them have any indication that they're text, other than the fact that this has an execution bit. So I can tell that this is going to be the segment where the text section gets loaded into because it has the execution bit, because you need to be able to execute your text instructions. So that's why text is loaded here. But there is no concept of like a text program header / segment. There's only a text section. So probably this peak text is just smart enough to like look at the segments. But that's interesting because like you don't need the segments to actually run the program. Like how does peak text actually know what the text segment is? Because the section header doesn't even need to be part of the binary to effectively run it. Like you can just strip that data out. It's metadata for tooling. It's not part of like the contract between the kernel and the program. It's not necessary. I don't know. It's something that it's an open question. Like how does ptrace peak text and poke peak and poke text and peak and poke data, how do they even resolve where text and data are in the condition where there's no section for those? Like in this situation, we have a section for text and a section for read-only data, but we don't have any indication from the segments which ones those things belong to. All right. Let's continue reading. So they do a peak text. What is the point of the peak text? It's to find the original value at the byte of the symbol that we resolved. And then we create a trap by taking the original value, anding it with F. Anding it with a negation of F. Why do we do that? That doesn't make sense to me. Anding with a negation of F. Oh, yeah, and it's a single byte. So that would effectively just set it to 0. So why not just use CC? I don't know. Seems like they're doing extra work here that they don't need to do. And then poke text. They then write the trap instruction into the place where the symbol was. And then they continue execution, which will then continue execution until that trap instruction is hit. So we wait on status, and then it goes into a if wait came back with stopped or stop signal is equal to sig trap, then we go in and we get our registers and we say, hey, the executive will hit the breakpoint. Here's all the registers. Please hit any key to continue. We then read in the character to continue. And then we do a ptrace poke text to put the original value back into memory. We then subtract 1 from the register, the instruction pointer register, to put it back before the trap instruction. We then single step that instruction, which may be multiple bytes. And then we wait with null. What does wait null do? Let's do a man on wait again. Yeah, this guy over here. So what if wait is given null? It's a nullable status. Let's see what null means. Does that just mean like I don't want to like read the status? I don't care. If W status is not null, it gets assigned into it. Okay, well, I guess null just means that you don't care about the status. So why does he wait for a state change in the child after he does the single step? I guess it'll get another signal, and he needs to just make sure that the single step has finished. That's why. Single step, the ptrace single step is not a synchronous call. It's a indication to the kernel that it needs to single step the child, but we have no guarantee that once the ptrace single step has completed, that instruction was actually single stepped. So we have to wait for it to get another signal, a sig stop, to then continue with our reinsertion of the trap instruction to reestablish the breakpoint. And then we go to trace, which is just a loop. I don't know why you implemented it as a go-to. I think you could have just done this as a loop. And then finally, if we hit something other than these stopped or trap signals, if the child actually exits, then we say, okay, we're going to exit the parent as well. Okay, and then the lookup symbol function is just a pretty straightforward iteration over all the sections, and we look for a section who has a type of symbol table, in which case we look into that to see if we can get the address of the symbol. I might actually come back to this code later when I'm implementing my symbol resolution stuff. Okay, using the tracer program. I'm not typing this shit in. There's no PDF for this program, or for this book, so I can't copy the code. Maybe there's like a online resource for the code that we can pull in. Maybe that would be good. Let me see if there's, usually they have like a website that you can download the code at. Okay, it's not here. Let me see if I can find it. Here it is. Preface. Downloading the example code. Here we go. So it's on the publisher's website. So let's just go here and go to packedpub.com. Wait a minute. You can download example code from your Account. I don't have an account. It's so annoying. I don't want to freaking create an account at their publisher. Alright, maybe they have it publicly somewhere. PackPub Learning Linux Binary Analysis. Data ebook. Oh, they do have an ebook. Download code. Here we go. Hey, it's up on their GitHub. That's nice. I might just like submodule this thing in. Yoink. In fact, I will do that. So if we go back here, I can say git submodule add help. So we're going to add name is source. Actually, no. I want the repository, and then the path will be book. What would you say source? Git status. Yay, git CI. And we'll say add book source as a submodule. Git submodule. So if I cd into source here, we should get, so we're in chapter 3. So this will be nice because I can actually read the source on stream instead of just reading it from the book. So they don't have the ptrace here. What chapter are we on? We're on chapter 3. I want the tracer program. I don't want a vulnerability program. Yeah, I don't want this. I think this tracer zip, if I unzip this, I think that's probably what we're looking for. I don't know why they zip shit. It's kind of annoying. Vim tracer.c. Here we go. This is what we were just going over. He actually has more stuff here because he has the get executable. His C style is like garbage. Like, what the hell is this thing here? If I write this, you see how much like the Clang lint or Clang formats cleans up here. All right, let's open up the make file too, and we'll do a little cleaning on that. So he just uses GCC. Okay. If I go back here, I'm just gonna say maybe I will add this. Nah, I won't add it. Yeah, we'll just ignore this for now. RM tracer because I want to rebuild it, and we'll make it. Oh, interesting. Implicit declaration function wait. So if we man to wait, he's gonna need a syswait header. Tracer.c. Go up here. He doesn't have syswait. Interesting. And make. Bam. Okay, so we got GC to behave. Let's run a tracer. Let's just run it on like bin bash. Why not? Oh, he has like a difference. Let's do that. I don't know what -f is. Let's open up the source code and figure out what these arguments are. So the usage was not very helpful. P unable to retrieve path. So this puts it in PID mode versus exec mode. We want exec mode. I don't know why he does like, that seems like the wrong way to do the usage. And also one of these is required, so like his usage is just like not syntactically valid. All right, we were looking for what -f was. So what is this thing doing here? He's doing a stir dupe to assign into the symbol name of the handle. and then breaking. So I'm guessing that's the function name to set a breakpoint at. So let's do dash E. Dash F will be like what, main, I guess? Bin bash is not an elf executable. This is the thing, like his code is just like so jank. Of course it's an elf executable. Type bin bash. Oh, sorry, file. Sorry, file bin bash. Elf 64-bit. It's an elf executable. So let's go into his tracer C, bin tracer C, and see why it's elf. So he's doing a stir compare. How does this fail? 7F. If we do odd AX, XA, and then bin bash, and we'll just do head. So we have 7F and then ELF. It's definitely 7F and then ELF. So I don't know why this is failing. The only thing I can guess is that this HMEM didn't get set correctly for some reason. But he does check map failed. What is map failed? Is that -1? Yeah, it's -1. Okay. mmap read private FD. It looks like he's doing that right. Maybe the FD was wrong. Okay. Well, it had to have been an open. Let's just add a printf here for printf, and we'll just say, hey, opening file path %s, new line, give it the h-exec, just so that we can audit what that value is. It should be the bin bash. Let's do a make, and then rerun this. Yeah, so it's definitely pulling in bin bash. It got past the mmap. And why is this? Let's just go ahead and printf out. We'll say %x, new line, and we'll say mem of 0 is equal to that, mem sub 0. And we'll do 1, 2, 3. 1, 2, 3. So this will give us our elf header, hopefully. And we can actually do a C on these. Make, oops, mem undeclared. What? Oh, h.mem. Okay. I don't know why I didn't catch that. h.mem. And why is this freaking out? Oh, somehow this got copied. I don't understand how that worked. There we go. Make, there we go. Rerun. Yeah, 7F ELF. Bash is not an elf executable. Okay, let's continue. Definitely. Oh, his logic's broken here. So we say hmem is not equal to that, or, I'm gonna say or, not and. So he just has like bugs galore in his freaking code here. Stir compare between that. If that's not equal. If you say and here, so basically this will be false, and so we say that'll be false and that'll be false. So both the operands of that and, the logical and, will be false, which means that it'll definitely be false, right? So how does it get true? Let me reread this. H.mem is not equal to 7f. That'll be false. The and will then force it to be false. I don't understand how this would, even with his bug here, I think he wants to have an or here to catch both of these, but hmem0 is not equal to 7f. It is, though. It is equal to 7f. So that's going to go to false, and the whole thing's going to go to false. So how does that even... All right, well, we'll just print out everything. So percent x on this one, I guess. Or b, we can do b for Boolean. Percent b, I think, would be Boolean. And then over here, we'll just do this. And then we'll do another one, and this will be the not stir compare is equal to elf. I guess I could attach the debugger too and like not do println debugging, but all right. Oh, this thing has, oh, it has spaces here? No way. Oh, the spaces were added because they're not escaped here. I gotcha. Okay, that should work then. There we go. Make, let's go and rerun it. So they're both false, and we have an and. So false and false should be false. Oh, it's down here, the exec flag. Oh. Read elf bin bash. We'll do -a. Pipe that into less. So he's saying the exec flag, or the type flag is not an exec. Yeah. Why is it a dying position independent executable file? I've never seen that before. It's clearly an executable file, but it reports itself as being a dynamic pi file. So, I mean, it's okay to have pi, your executable be a pi position independent, but that almost seems like it means that it's like a dynamic shared library, which it totally isn't. There's like, what I'm learning, the more I learn about ELF and how Linux loads and executes binaries, the more I'm starting to realize is that the division between like dynamic shared libraries and executables is very kind of like gray. It's not a clear division. It's not like you have executables on this side, shared libraries over here. That's the way we typically think about it. But you can see bin bash is reporting as a shared library, but everyone knows bin bash is an executable. And then you have things like user lib libc.so.6 that if you run it, like that's a shared library, but I can just exec it and it runs as if it's a binary. And if I do read elf, let me do the same read elf on that. User lib libc.so.6. So you look here, but this is a dying shared object file versus a dying position independent executable. So what I'm learning here is that I need to open up his code here for tracer C, go up here where he's testing, actually down here, where he's testing for exec. Where is it? Down here. If it's et exec here, So he has a dyn here, but there has to be like an ET pi. Like, how do you know that it's an ET dyn shared object file versus ET dyn position independent executable? How do you know the difference? Like readelf clearly knows. Readelf header user libc.so.6. It knows that that's a shared object file, and it knows that bin bash is a position independent executable file. So what is the delta here that allows it to understand that? Is it the actual value? Because it looks like it's the same, dyn and dyn, for the type. I guess there's a magic value here that's different. If we look here, we got the elf and then 211, and then this one's 211, but then has a 3 at the end of it. Where was I reading about this man? Let's do man elf. And class data version. That's what those things mean. Class data version. Okay. Let's search for pi here. I don't see anything about pi. Let's search for position independent. No. This man page does not have it. Man dash a elf. Is there? No, there's just one man page on elf. I don't know, man. If we go back up here and look at the struct for this, so we have 16 bytes that are just the identifier, and then we go immediately into a 16-bit type. So if we do OD here, this is all gonna be that ident, and then the type is 3 here, because that would be 16, yeah. And then if we do the same thing on user share, or sorry, user, what was it? User lib, libc.so.6. So this thing has the same value here. So it's not that type. You can't key off that type. How does it know that it's a position independent? I'm gonna have to use ChatGPT here. Let me close out of all this, and actually need to check my calendar here. Okay, I got a couple more minutes before I have to break for lunch. So if we ask ChatGPT, because I'm out of ideas here, we'll do our read elf on bin bash and this, and then we'll copy all of this into ChatGPT and say, I don't understand how readelf knows that bin bash is a pi executable but still has dyn set as the value of its type in the E header. EDYN is overloaded, obviously. The key point, shared libraries and pi executables both use EDYN. This object is position independent and meant to be loaded as a flexible base address. So how does readelf distinguish them? Use additional heuristics from the rest of the elf file, mainly the presence of an interpreter, p interpreter. Pi executables have a p interpreter segment. Shared libraries typically do not. If that exists, it's an executable, even if EDYN, entry point usage, pi executable, meaning entry point program start. Okay, so yeah, we'll have an entry point, right? but both of these have an entry point because again, libc is an executable shared library. This stuff is like, this is what I'm saying. It's just like totally like, there are no very clear distinctions between these different. I mean, you can have a Dyn typed shared object that does not have an entry point, does not have a interpreter segment. That is clearly what you would think of as like a normal shared object. And then on the right hand side, you can have an executable that's marked as exec for its type, has optionally an interpreter segment, definitely has an entry point. And so these are two kind of poles of the spectrum. But then you can have one notch over from a pure shared object. You can have a shared object that you can execute because it has an entry point address. And my guess is that it probably has an interpreter too. Let's see if it has an interpreter segment. Let's do -a and pass this into less. Let's search for interpreter. Yeah, it has an interpreter. And this is a libc shared object. So the interpreter alone is not sufficient. We'll say grep-I interpreter. But the libc example I gave you also has an interpreter. df1pi does not have df1pi. Let's grep for pi here. Definitely doesn't have that. If I go to bin bash here, it does have in the flag section something called nowpi. Pi. So this is in the flags dynamic section at offset. Contains 26 entries. Wow, so many relocations. I guess it's bash. You'd assume it has a lot of stuff in there. Alright, I need a break for lunch here. So yeah, I guess there's this dynamic section. Flags has like a pi flag. I don't understand that because you can also have position independent. Like all shared libraries are position independent because they have to be mapped somewhere. Maybe this constant or this value here is pound define. I need to look up. I'll just Google for it. Why is this only one if it there's DT flags one? Pi determines if executable is a position independent executable. Seems to be information only since not used by Linux kernel or libc. So it's basically used by readelf. Like readelf can read it and be like, oh yeah, I know it's a position independent executable. File type as explained in Stack Overflow. Interesting. Please go away ads. Oh, LSB versus pot. No, this is they're both LSB. Okay. Yeah, before it printed shared object for pi. Yeah, both Pi executables and shared libraries are position independent and can be placed at randomized memory locations. So that's interesting. That means that, and this is not something that I've really considered much in depth before, is in order to take full advantage of address space layout randomization, like your program needs to indicate to the kernel that in addition to being like an executable, it is position independent executable. And it does that by saying, hey, I'm a dynamic library, or I'm dynamic, whatever that means, since it's overloaded. But I'm also a position independent executable. And I guess that happens with both libc and with bash. When you execute them, when you exec them, I should say, the kernel does address space layer randomization on it because it's position independent. Both of them are position independent, but one of them is marked as a position independent executable. And then you have like programs that are just traditional executables, in which case it can do stack randomization for ASLR, but it can't do ALSR on your text, on your data, on stuff like that. So what does that mean? Well, effectively that means that when I run bash, I should get random mappings for where its text and data segments are located. So this is a cool test here. We can run bin bash c, and then inside the shell, we're going to say cat out our proc $$. And then we want to cat out maps. And what this will tell us, so our executable, so we want everything that's like bin bash, like the text segment for bash itself is what we're interested in, to see if it does ALSR. And we can see already it's doing address space layer randomization. It's all the way up in like 5F or whatever. Whereas if you ran like a normal program, it would have these mapped at very low ranges at 4,000 hexadecimal. It wouldn't be up here. And every time we run this, so I'm going to do a little greppy grep here. So grep for r-xp. And we also want to just grep for bash. So every time I run this, you could see, actually no, it isn't randomizing where it lands in memory. I thought it would. Interesting. What about the data segment? I figure with a Pi executable, you would get randomization on all of these here. Let's just grep for 5.5. Because that seems to be the address prefix. 55F3. Are any of these randomized? Let's output this whole thing to temp A. And then we'll do it again for temp B. And then we'll do a delta between temp A and B. There's no delta. Okay. So it's not doing very good ASLR. If it's doing address ASLR. Okay, well let's do like a normal program. So not bash. I'm just gonna write a simple program here. I'm gonna go back all the way to chapter 03, I think it was. No, this isn't K and R. What am I doing? I did this in the totally wrong location. I did this in KNRC. I need to fix that. Oh, that's a bummer. All right. We need to jump over to, this is, did I push this already? No, I didn't. Good. So, not that I couldn't force push it, but let's jump over to learning Linux binary analysis. This is where I wanted to put it. So we're going to MV, or we'll do our git submodule add this whole thing. Can I just copy this command? Copy, put it there. Okay. And then we're going to say MV source into learning Linux binary analysis source. And here I'm just say rmrf source. Do the MV, rm.get modules, get status, get add all, get CI temp, get rebase onto origin master, and we want to do it interactively, and we want to squash. And if we do get LGA here, we should, oh, I didn't squash it correctly. Actually, you know, get reset, get rebase abort, get reset hard to origin master, and then get LGA. Okay, so now everything's back to where we wanted it. Over here now, get CI, I'll actually take my commit message too, which was add book source as submodule. Put that there. Okay, so now we're on the right repo here. This thing I need to get rid of. And here I'm going to make dir chapter 03, cd into that, and then I'm just going to vim up a test sleep dot. Actually, no, I should have a sleep program in KNR. Jump over to KNRC, rip grep for sleep. Really? There's a pause. What? I clearly have used that. Okay. Well, we'll do it here then. Pause.c, and we'll just have a main, and we're just going to call pause in the main, so we can test the ALSR on this. And we do man2 on pause, which is going to be Unix standard, pound include Unix standard std.h, pause. Yeah, it should be fine. Okay, so let's go back over here, find a make file. CP, I don't want any of those. CP, let's pull from, we were recently in nodecc 00 makefile. Yeah, let's grab it from there. Then makefile, and I'll just delete all of this. Everything else looks good to me. And we'll do make here. Vim makefile. Oh, I need to move this into chapter 03. Go in there myself. Vim makefile. Yeah, I don't need this build out thing either. Make. There we go. So now I can say build. I also need a vim.get ignore for build. And then we'll run our build test pause. So if we run readelf on this, it says that it's a, oh, this thing's a position independently. I don't want to do that. Maybe if I just use GCC instead of zigcc. Oops. Actually, I can do this as a parameter. we could say make cc is equal to gcc, make clean, and then readelf. It's still doing a position independent executable. How do I not generate that? I'm actually surprised that this came out this way. How do I generate from a CC a regular exec type versus dyn pi? I think I just say no pi or something. Yeah, we'll do this. Give it all this. I think it's like the flag is like no pi or something. Yeah, no pi. No pi f no pi. So then make file here. Add that to the flags. Oops. Copied it wrong. Alright. I actually didn't know that it did pi on executables by default. So if we make this, make clean, oops, make, and then we run build, or sorry, I need to run readelf on it. Readelf on that. So now it comes in as executable file, and it has an entry point address of this location. If we go back up here, the entry point address was 1040, which doesn't have the offset, the virtual address offset in it, which makes sense. So now when I run this test pause, so all of this to test out the map on this. So if I do ps aux grep for test pause, which is this PID here, and then I cat out proc that PID maps, you can see these maps are all in these lower addresses here. I actually might do two make files. We'll say pi and no pi. So this one would be pi and that would be no pi. And then in here, I'm just gonna say, hey, I don't really care about doing this. We'll do build slash pi, test pause pi, and no pi. And then in here, we'll just name this test pause pi. Oops. And then we'll do test pause dot c. And then this will be pi flags. And then we'll do one with no pi. No pi. And this will be no pi. Okay. Make clean and make, and then if we do our, make this a little bit bigger, our readelf header on build test pause no pi, so that's a no pi, and then a pi is a pi. Okay, so if we run build test pause pi, oops, and then we do our grep here, grab this, cat proc that maps. So this is with pi, it goes high in this high address range, whereas no pi, it's the low address range. But what I would like to see is this to be ASLR'd. So if I grep this for, again, like 55E1, and then pipe that to temp A, and then we'll do another one here where we need to do our grep here. Oops, sorry. Do our grep here, grab this, and then we'll just rerun this here. Oh, I forgot to. All right. Oh, damn it. I did it on A again. All right, let's just do it one more time. Do a grep, grab the PID, and change that to B. Put this here. And then run our delta between temp A and B. And there's no delta. So the pi executable is at a higher address that appears to be random, but I think what is happening is this random address for the pi executables, it probably gets set at Linux's startup time, and then it doesn't get changed until the machine restarts, because obviously it's not done per process. Let's just ask ChatGPT if it agrees with that. So when running a pi executable, the text is mapped to a high address, and we'll just give it this. But that address doesn't change per invocation of per exec of the binary. When does this change? Is this part of ASLR? Does the kernel randomize these addresses at any point? One of these is almost true. ASLR is disabled, most common in debugging environments. Okay, let me check that. Cat proxys kernel randomize VA space. Why does that not want to complete random all eyes VA space? There we go. So it's set to 2, which means full ASLR. That's nice. You're observing a fixed random C per process tree. Even with ALSR or ASLR enabled, fork inherits memory layout entropy. Repeated execs under the same parent can look stable in some setups, less common but happens. Okay, so what I can do to verify that is to do the same process of invoking this thing, but do it in a different shell. Different terminal here. So let's go to 03. I'm gonna do this. Oops, didn't copy. Do that. Not in the right chapter 03. That one, yeah. Now over here, I'll do my grep again for that. Grab the PID, and then we'll do this to B. And yeah, we'll leave the 5.5 there. And now we'll do our delta. Same delta. If you're using a loaded debugger that disables randomness, no. Sandbox entropy constraints. None of A through D apply to my situation. But you're not actually observing multiple independent randomizations. You're likely reusing the same process context or some same deterministic entropy seed window. Pi base is not per file execution in isolation. Even though it feels like each exec should pick a new random base address, the real model is the kernel uses process context-based entropy source, not a pure fresh random number per exec guarantee. That matters more than people expect. The key hidden mechanism. Okay, I don't really give a shit about reading about the entropy. You are repeatedly executing a binary in a way that reuses the same entropy context, often via wrapper, tracer, parent process loop. Tracer, no. I don't know. I don't think ChatGPT really knows. Yeah, this is a bunch of stupid shit. I don't think ChatGPT knows the answer to this. Okay, well, that was enlightening. We learned about independent executables, which are different from position independent dynamically loaded shared libraries, and are different from traditional executables. My assumption going into the session today that I have never questioned is that executables are just marked as executable. And that is the assumption of the tracer program that's part of this book. But the reality is that Linux user space has moved on to generating position independent executables. And we saw that in GCC and ZigCC, which uses Clang, that they all default to using position independent executables. So yeah, that's just something to keep in mind now, that it's going to be harder to tell the difference between executable and shared library using the ELF headers. Cool. All right, I'm going to hop off here, grab my lunch, do my hit, and then I have a meeting at 1:30 that I have to do. So I will be back on shortly after that, probably around 3 for a 2-hour session. And I'm just going to be doing more reading about binary analysis and ptrace. And hopefully we finish this chapter today on ptrace. Cool. All right. I'll be on later. See ya.